Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so thanks everybody for coming. So introducing Mark. Mark's no stranger to RISE. In fact, his paper here is joint work with Chris Bird, just showed up. So I'll let him take it away. Thanks,
okay,
Mark.
great. Well, hi everybody. Thanks for the introduction, and thanks everybody for coming, and I guess people watching remotely, thanks too. So today I'm going to be talking about some work that I did with Earl Barr, who's a postdoc at UC Davis, Chris Bird, who's here at MSR. And we basically did sort of an empirical study of the structure of the program Heap. And so the motivation for this is, well, okay, the slides work on my, click on that. Hey, there we go. Okay, the motivation for this is, for me, most of my work has been on sort of, tools and techniques for either static or runtime analysis of the program Heap and aliasing, these sorts of structures, applications for this in optimization, memory management, and so forth. And in doing this, I spent a lot of time sort of looking at, well, what properties do people say are important about the heap? What properties do they try and extract in these analyses? What properties do they try and leverage in these program optimizations? And how do these things go? And can we sort of distill the properties that are used in this wide body of literature down into a couple of core principles that are sort of general, applicable, important things. And in this process, I sort of process of discovery for me, because a lot of things that I looked at and I said, oh, this is, looking at this code, this is an important property, this is going to be fundamental to understanding what's going on in the program Heap, just turned out not to matter. And some things that I thought, oh, this is, it might be interesting, but it's fairly incidental, they turned out to be fairly important into getting sort of the right structure and predicting things correctly. And so really what we wanted to do in this study is we wanted to sort of look at sort of a step back and say, well, look, can we look at sort of these concepts that people are using, that I've been using, and look at some real large programs that represent real world workloads and say, look, are these concepts, perhaps too simple to describe the reality of what these programs are doing? Are they more complex than is actually needed to get useful information out of these? And so their extra sophistication is really not giving us any value. It's just taking us computational cycles or, increased implementation complexity and not getting us anything useful. And, the hope was that, okay, maybe there's a nice simple set of sub-concepts that categorize the majority of what's seen in practice, right? The hope is that most heap structures and most programs build sort of this consistent set of heap structures and maybe have small specialized structures that they use, and not every program builds an entirely different sort of looking heap. So what did we do? Well, we wanted to try and not bias this study too much, and we wanted to look at this in just sort of a general, from base principles way. So we said, look, we're going to pretend these heaps are created by some unknown process. We're not going to look at the source code at all. We're just going to run the program. We're going to take a heap snapshot. We're going to start out with some set of features we think are important. We're going to express relationships between, sort of this graph structure we got and these properties. We're going to do some measurements. Some things we'll say, okay, we're able to categorize this structure and this structure and this structure. And some structures we'll say, well, we don't have any way to express these. They fall into some unknown thing. If that unknown set is big, we'll sort of look at these heap structures that are in the unknown set, hypothesize some new features, repeat again until we sort of feel like we have a good coverage of general things, and then we'll see where we are. And hopefully at the end of this set of features we have is fairly small, fairly reasonable, and this uncategorized set, is negligible. So we'll see how that goes towards the end. Yeah?
Before you go on, can you go back? So if you ignore the source code, the type declarations give you some...
Yeah, so we don't fully ignore this. We're going to hypothesize features that, are relevant to some programmer-related concept. We don't want to just be too general. So we're trying to minimize our bias here. So we're going to look at types. We're going to look at field identifiers. We're going to hypothesize things that are going to be relevant to a programmer, such as aliasing or immutable types. We'll say, okay, let's base our definitions on these things. But we don't want to start looking at the source code and say, oh, we're building this with recursive calls, or we're building this with whatever. So we want to just be as general as possible. And I think it'll be a little more precise as we go on and introduce the measures and stuff. So what's nice about this, well, doing this runtime study, we can easily experiment with a range of sort of definitions and identify these features just by looking at what pops out that we weren't able to categorize earlier. We have high confidence since we're running these on large programs and over a fairly reasonable benchmark corpus that they actually are useful in practice. We're sort of not, since we're not looking at the source code, we're not constrained with issues of, did I get a lot of uncategorized features because I didn't have a way to categorize them or because my analysis was imprecise? We sort of avoid that whole problem by using concrete execution. And, going back to my experience with static analysis, we avoid all the issues with reflection and threads and all that good stuff. We just run the program, take some snapshots, and we're good. So what is the artifact we're actually going to use here? How do we snapshot the heap and then turn it into this artifact that we're going to measure? Well, there are two ways to sort of look at this, and previous work has explored both of them. But the majority of the previous work has sort of said we're going to compute metrics on individual objects. So we're going to take an object, we're going to measure its indegree, we're going to measure whether or not it's aliased, whether or not pointers it has in its fields, alias other things, is it part of a linked data structure, whatever. But and this is sort of a hypothesis we're going to make. My experience is that developers aren't really thinking in terms of individual objects when they're building the code. They're thinking about the roles these objects play in a structure, how these larger structures fit together, and how these compose together to sort of, be the representation of some concept in the abstract problem space that the program is attempting to solve. And so we're going to sort of hypothesize that these roles that the objects play are encoded by how the objects, their types, of course, and how these objects are stored in various data structures and can be referenced in various ways by the programs. So we're going to attempt to sort of examine the validity of this hypothesis later, but we're sort of making this assumption from the get-go in how we do these measurements. So what we're actually going to measure is an abstraction of the concrete heap. And we're going to take, it's based on this stored shape graph approach. So we're going to take the concrete heap, we're going to group the objects into equivalence classes. Each of these equivalence classes is going to become a node. And then all the pointers between objects in the same equivalence class and objects in another equivalence class are going to become the edges in the graph, right? And this is a nice natural way to represent a lot of these sharing properties. It's been used a lot before. The only thing is there are some properties that we're going to be interested in that can't be encoded just in the graph structure. So we're going to add 2 extra sort of annotations to the graph that allow us to express a little bit more information that's interesting. So a big question is how do you group objects together? We say, well, we have a bunch of objects in the heap. We need to produce equivalence classes for our graph. How do we do that? If we have too many equivalence classes, basically we're going to have objects that all are really equivalent from the programmer viewpoint, but in multiple equivalence classes in our abstraction. And, well, we're basically having a bigger graph with more complexity that actually isn't capturing any information. So that's not too good. If we have too few nodes, we have lots of objects that are in 2 actual distinct equivalence classes from the programmer viewpoint. We're merging together, so we're losing precision. So the question is, well, how do we pick this trade-off that works well? A lot of previous work has sort of done this partitioning by looking at the allocation side of objects, the type of objects, maybe some object sensitivity, so you sort of generalize this allocation side information. And I'm not a big fan of these fixed naming schemes because you sort of have to, before you even start, you have a finite number of names, and you have to assign every object to one of these finite equivalence classes. We want to have as many equivalence classes as we need to express all these sort of conceptual components that the programmer has in mind, and no more. So we want to basically dynamically generate as many equivalence classes we needed based on some, the runtime structure. And so we're going to have this notion of indistinguishability between 2 objects, right? And we'll say, okay, it has 3 parts. 2 objects are going to be indistinguishable if they're part of the same recursive data structure based on type information. So here's where we're using type information a little bit. If they're stored in the same collection or array and they have the same type, so 2 objects in the same array of the same type are sort of indistinguishable to the programmer, or if they have indistinguishable predecessor objects and they have the same type and the same predecessor fields.
So if you have 2 linked lists, they're distinct under this definition?
They'll be distinct under this definition as long as they aren't, connected together somehow. Right.
2 distinct linked lists are distinct in your representation.
Right. So basically the idea here is that, if you think like a point object in a ray tracer, right? You'll have many point objects. They're all the same class. They're all is a instance of points, but they'll all be you might have some representing the vertices of some triangles that you're rendering. You might have some that are representing the bounding boxes of the space decomposition tree you're using. So they're all, representations of distinct concepts in the problem domain, right? So we sort of want to capture that. So here's sort of an example that I'll use as a running example through this. We have a simple program that manipulates arithmetic expression trees, right? And so we have some, expression objects. They all inherit from some expression class. We have add, multiply, subtract. We have some constant objects, so these little consts hanging off there. We have some variable objects, and something you might want to do a lot in this is if you have the same, you might want to intern these variables in some sort of table so that if you have multiple references to the same variable, they all share the same reference. And so in our case, we have the variable objects in this little variable array, and sure enough, we see that two terms in our expression tree both have their left field pointing to the same variable object here. So this is shared like that. And so if we apply these indistinguishability principles, well, we see the first one says, OK, here's this recursive backbone structure. We say, OK, look at the variable objects. They're both in the same array, and they have the same type, so they'll be indistinguishable. And the constant objects are of the same type, and they have indistinguishable predecessors. So we'll group them into the same equivalence class, conceptual component as well. And so the resulting sort of abstract graph model that we're going to do the measurements on looks like this, where we have one node for the conceptual component that represents the backbone of the expression tree, one node that represents the constant objects, one node that represents the variable objects, and then our variable array sitting off there. Yeah?
So the work that was done with data structure analysis, it was a static analysis that was done by Chris
Latner and Advent, yeah.
Yeah, so does it come up with the same distinctions here, or is it different?
It is a little different. They basically do a local, if I remember correctly, I believe they do a local points to analysis first to sort of compute a sort of partial points to graph for each method. And then they do a sort of top-down, bottom-up, context-sensitive but flow-insensitive approach to unify these various local points to graphs into the global points to graph, or the global points to graphs that they need. So again, this goes back to the fixed naming versus sort of this ability to generate partitions on demand. So we'll generate as many const partitions as we need, even if they're all allocated at the same site, but they end up being used in different places, right? We'll just look at the structure of the graph and the types in the graph, not necessarily the allocation sites or anything like that. So you'll get, depending on the exact code, you'll get similar structures, but I think this is in general going to produce a more refined result. But yeah, I can talk about it.
So you're going to keep track of how many objects are in that abstraction of add, multiply, subtract?
For this study, we don't. In this study, we just wanted to look at the structure here, but certainly you could in the abstraction, and we do that in some other work where we actually use this for doing some memory use analysis. Yeah. Okay. So any other questions? Or okay. So you notice here that, so we did a nice job of sort of identifying the components that are going on in this heap and that are, the various parts of the heap that the programmer is using for different things, but we've sort of lost some very important information, right? So now, for instance, we just have some sort of self-edge on this add mult sub, right? It doesn't really give us information whether or not this is a tree or a list or some sort of cycle, right? So we'd probably like to recover that. So the first additional property we're going to have is some notion of layout for these regions with self-edges. And we're going to have a really simple way to do this. You can either be atomic, there's no internal connectivity. You can be a tree, so you're a binary tree or a k-ary tree, or you can be a cycle, right? And we're going to order these so a cycle or a tree is sort of a degenerate cycle, okay? So really easy. Node with an atomic layout has okay. So I said this, and yes. So that's a pretty simple set of shapes to label these things with. And so our example here, we say, okay, well now we'll say this has a tree layout. So this means this is a k-ary tree over these objects. The other thing we sort of lost some information on was this sharing between pointers that end up being grouped into the same edge, right? So this edge basically represents some set of pointers that are stored in the add, mult, and sub objects in this component that point to const objects in this component, right? And if you remember back from our original abstraction, let me go back a little bit here. Well, we see that the variable, our intern array, has, each index in this array points to a unique variable object, right? Although these variable objects might be shared by multiple elements of the expression tree. And here, we've sort of lost that information. We say, well, there's some pointers from the expression tree to variable objects. They may or may not share. And there's some pointers from the variable array to variable objects. They may or may not share. So we want to refine this a little bit. And we're going to refine this in a very simple way.
So
yes?
Can you go back?
Sure.
If you have back pointers, then everything becomes cycle?
So it'll actually, the way we detect recursive structures is a little subtle, but it actually allows us to distinguish between, let's say, things that have recursive types because they're building some unbounded recursive data structure versus things that have recursive types because, let's say, each variable needed to know, let's say there was some larger context about where this expression was defined, and each variable needed to know about its definition context or something. And so you had this back pointer from the variable up to the definition context. That's sort of the example you're thinking of?
Well, just would you label inside, if each of those had a back pointer, you'd label it cycle, or would you still label it tree? Are you going to refine that a little bit?
Cycle. So this is one of the things we looked at. We started out, we said, let's be really simple. It's a really simple tree, or it's a cycle. And maybe we could refine this to be doubly linked list, or a tree with parent pointer. But we found out, and we'll get into the details here, that it really didn't make much of a difference. So we sort of left it as that. So this notion of injectivity. So where each edge represents some set of pointers. And we're going to assign it either injective or non-injective. And if it's injective, that says all pairs of pointers that this edge represents do not alias. They point to different objects. Okay? Or they may alias, so there may exist a pair of pointers that might point to the same object. Now, I want to point out that this is a really, really strong sort of definition in a sense that the notion of injective is about the strongest property you could assert for non-aliasing. It's saying all pairs of pointers don't alias at all. Or, a very, very weak statement, there might be some pair of pointers that alias somehow, but I'm not giving you any more information. So this is a very strong property that we're asserting there. So if we look at how that sort of refines our structure here, we've basically split this one edge to now distinguish between the R pointers, which are injective, pointing to the variables. So each R pointer in the expression tree points to a unique variable. And the L pointers, which actually may alias some of the variable objects. Okay? So then we're going to use these properties, and we're sort of going to think about, as we go through these measurements, some general questions. Well, okay, how many components are used in practice, right? It's just sort of a general structural question. And does this number correlate to the number of objects or types used in the program, right? Is there some sort of one-to-one relationship between types and components? How prevalent are some idiom-specific things, like are immutable types and components used a lot? How often do we see the singleton pattern? Indegree distribution, just a simple graph structural property. Tree, cross, back edges, we want to classify these. And then we also wanted to look at some more sort of application-specific questions, a little more motivated by the research. So, are heaps built up as sort of recursive data structures, or are they built primarily by aggregation of sets of objects? How prevalent is local ownership? There's a lot of work on ownership type systems, ownership annotations. And we're going to look at sort of local ownership. And this is, whereas ownership is a transitive reachability thing, we're going to define local ownership as just, is this pointer the unique reference to the object it targets? So basically, global ownership implies our local ownership, and it's a little easier to measure. How prevalent is injectivity? This is a very strong property. I mean, maybe we don't see it very often. Maybe it's too strong. And when we do see things that are not local owned, well, why is this sharing occurring? Can we categorize this in a nice way? And we want some sort of not just qualitative information, but we want quantitative information about sort of the prevalence of these various things. Yeah?
Maybe you're going to get to this about your methodology for making these snapshots.
Yes.
The previous slide, or before that one. So it just happened that it was the L pointers were non-injective and the R pointers were injective.
And it was just luck, right? And if we ran it with a different input data set, they might both be non-injective, right? Yeah. So yeah, I'll get to the methodology in just a second. That was the next slide.
So one more question on this slide?
This one?
No, the one you went from. There, sorry.
Yeah.
One more, 16.
Okay.
What's the difference between local ownership and injectivity?
So in this example here, right, so here this R field, this edge represents injective pointers, right? In the sense that we're saying it's thin and light. So basically, every pointer in excuse me. This represents some set of pointers, right? And we're asserting this is injective, so that means that no pair of pointers in here alias the same object in here.
Right?
What?
For the L pointer.
For the L pointer, we're saying that there exists some pair of pointers in here that may alias on the same variable object. Whereas the R field, no pointers alias the same variable object.
I thought it was the other way around. Aren't the bold, isn't the bold an injective?
The bold is non-injective.
Okay.
Sorry. Yeah. So the difference between, so in this case, this set of edges, okay, is injective, right? And there are only one incoming edge to the set of constant objects. So that means that, well, there's only, none of these pointers alias, and there are no other pointers that refer to any of these constant objects. So we know that each constant object is referred to by at most one pointer in this edge, right? Whereas in this case, well, this edge is injective. So each pointer in this edge refers to one variable object. But there are multiple incoming edges, so there might be sharing between sets of pointers in the two edges.
Okay. So then what's local versus?
Const would be local.
Yeah, so const. So this edge is going to be the local
Okay.
ownership of these, but these variable objects are not going to be locally owned by anybody,
Okay.
right? And I'll show some measurements, and we can talk about it a bit more in a second. So the methodology. So what are we going to do? So we're going to do runtime extraction. We used the IKVM cross-compiler to take a number of the benchmarks from the Da Capo suite and convert them to .NET bytecode. They're fairly large programs. We didn't take all of the Da Capo suite. We took 6 of them, so like the XML parser, there's program analysis, text indexing, document processing. They're reasonably well-written, object-oriented code. They were selected because they sort of represent a variety of real-world workloads. They have nice inputs that are, in theory, exercise large parts of the code. So this goes back to sort of the coverage issue. We felt pretty good that these were going to, produce some interesting varied heap structures and exercise good chunks of the code. Now, what we're interested in is we wanted to sort of simplify our lives. Rather than trying to find do these measurements on sort of universal quantified over all points in the program and all objects in the program, we wanted to look at these properties when objects were in their invariant state. So we're going to do our sampling at the entry of every public method. We're going to do some randomization on that, but we did some experimentation, and it doesn't really matter in the results. We're going to produce heaps where all the objects are in their invariant state. So at a public method, we're going to start with the local variables and any in-scope static variables. We're going to walk the concrete heap, take a snapshot of this, and then transform this into its abstract representation, and then accumulate. So we're going to do the join of this new snapshot with all the previous snapshots from this public method, and do this for each method in the program, and accumulate all of these over the run. And this is what we're actually going to perform the measurements on.
Okay, so you're not going to union across methods. You're going to keep it unique.
Yeah,
one per method.
One per method, yeah. And then we're going to do, okay, so basically here's our workflow. So we take the program, we instrument the bytecode, we execute it, take the snapshot, we do this accumulation, we might adjust the sample rate. If we're not seeing any new state, we'll back it off a little bit. But as I said, we tried running it with full sampling on some smaller inputs, and it didn't really change the results at all. And then we're going to take this accumulated set and do a measurement on this, right? Now, the interesting thing with a measurement is, what do you measure, right? Well, we can either compute the rates of these various properties on the nodes and edges we see, or we compute it on the types and fields we see, right? And the nodes and edges is obvious, right? We just look at each graph, count how many nodes satisfy a given property out of all the nodes, and add that up, right? The types and fields is a little different, because now you sort of have to, again, look at each type in each node that occurs in each method, and basically take the or the and of each property over all of the measured values you see, right? Now, depending on the application you have, you might be interested in, like if I'm doing program analysis, well, I care about the number of regions and the number of edges that satisfy a certain property, or how prevalent this property is in these, because I'm dealing with nodes and regions in the abstraction. If you're designing a type system, well, then you care about these measures in terms of the number of types and fields, because that's what you're trying to specify. So we measure in terms of both. And we see slightly different results in the two, so it's kind of interesting. A couple of, sort of the default boilerplate slide about some warnings. There are, of course, some limitations in what we're doing here, right? This is a runtime study. We're looking at object-oriented programs written in a memory-managed language. And so the results we get here, there are some things that will generalize, some things may not, but some care should be taken. This probably isn't representative of low-level OS code. It might not be so representative of how functional programs build heaps. And even if you look at how C++ programs build these data structures, they don't have memory management. So the notion of ownership and sharing and lifetime might be fairly different than in an object, a memory managed language like Java or C++, C#, where you don't have to worry about these things. Further, we're doing an evaluation over one suite of programs with the specified abstraction. So, as Mike pointed out earlier, we might miss some interesting behavior if this isn't exercising code or isn't exercising certain programming idioms that are out there. And we might be masking some interesting information by the abstraction. Now, we picked the da capo suite because, in theory, this should be a fairly representative set of benchmarks and inputs. And if we do mask information with the abstraction, that's just going to reduce the fidelity of the measurements we take. It's not going to introduce any incorrectness, just might reduce the precision a little bit. And we'll see that, in fact, we seem to get very precise information. So this does not seem to be a problem. So now I'm going to just sort of talk about some of the results, the measurements we saw, what I think are some interesting features that we pulled out, and some implications there. Now, we meant this to be sort of an empirical study for people to use in their research, look at, find out what they find is interesting. So I'm going to sort of point out things that were interesting to me in my research and my biases a little bit. But if anybody sees something odd in some of these slides that they want a further explanation of, or think looks interesting, feel free to interrupt and I can answer questions or comment or whatever. So the first thing is just sort of some of these miscellaneous properties. So we have our 6 benchmarks here: Antler, Chart, FOP, LU-index, PMD, and Xalan. We have the number of objects in the largest heap snapshot taken. We have some information on the types that are seen. So the total number of types that we saw instantiated in the heap, this differs from the total number of types declared.
So is this from one input or multiple? I think there's 3 inputs.
Yeah,
right?
we ran the default medium input for all of these.
Okay.
Yeah. So the number of types that we detected as being singleton. The number of types that we detected as being global intern types. So this is like our variable array. So we basically had a static field that points to a collection that has objects of this type in these, and we only see these objects in this static collection. And then we have some information on the components. So how many components were identified for the largest snapshot. The number of components that consisted only of immutable types. So that would be like system.string, system.int, this sort of thing. And the number of components that consisted only of system types. So that could also be like, hash set, arrays, whatever. So what I thought was sort of interesting here is one of the questions was, well, how does the number of types relate? Yeah.
So you distinguish between the libraries and the application itself in any way?
Yes. So in the abstraction, we treat the libraries a little carefully. Rather than basically exploring the internals of how a hash set is represented, we recognize it as a hash set. So it's an opaque container from the programmer's perspective. So we basically just, rather than sort of saying this is a object that is a hash set with a hash table with buckets hanging off, we say this is an opaque thing that represents a hash. It's like a hash set object. It's atomic.
That for all the built-ins?
For all the built-in containers, yes. Right.
And does the JIT compiler come into play at all in these measurements?
In what sense?
I mean, if the JIT were to run while you were doing your measurements, right, you'd be measuring the JIT as opposed to the application again.
They're using .NET, so they don't have that problem.
We use CCI to...
Okay. Oh, I was thinking of JITs. Okay, yeah. I'm sorry.
And also, yeah.
But if the JIT is like a JITs, the JIT is another Java program.
Right.
So it's got its own state, right? So that's my point.
So here we're actually sampling only at public. We're using CCI to rewrite the bytecode program to add instrumentation code at public methods, right? And we freeze all threads. We make sure that nobody's doing anything, and we only walk objects that are,
Oh, that is-
that are visible for that method, right, in the application space.
Oh,
Yeah.
so you're sampling the application space for the local objects.
And everything, the local variables and everything reachable from those.
Right. But,
So-
but there's the other part of the heap.
Right, which is up the call stack, which we're
Right.
not looking at because those objects might not be in their, invariant state.
Scope or invariant.
Yeah, and so we want to basically compute the sort of invariant properties for the objects.
So do you have a rough sense of the fraction of the heap that you're actually looking at?
And the largest, so we should get near the max heap size because we sample at every public method, right? So,
It's just when they're sampling each part, right? And how often.
yeah.
Yeah, again, it depends on how much state the runtime has that,
Yeah, so rough ballpark figure, the max reported mem usage for the DiCapo benchmarks, we seem to be about 3/4 of that. So we're missing something's floating around out there that we're not getting, but we seem to be getting, quite a bit of stuff.
And the percentages are with respect to objects, not.
The percentages, so these
heap?
percentages are with respect to components, and these percentages are with respect to the types.
Okay.
So basically what we did here is we said we found 606, nodes, conceptual components after we did the abstraction, right? We looked at each of them and we found out that 25% of the 606 were only immutable objects in that component.
Okay. So it'd be interesting to compute that as a percent of objects in the whole heap and also a percent of bytes in the heap, right?
Yes. Yeah, I believe, I could swear I've seen work that's done that sort of study before, but I could be totally
We have.
mistaken. Yes, okay.
But we have different metrics, so it's interesting for you to do it, right?
Yeah. Okay.
Can you just explain the typing for white typing for 0 in the first one?
For Antler?
Singletons is a person unit. So.
Right, so basically this says, okay, we looked at all the, so there are 606 components, right? These were created using 63 types. And we looked at the number of components that were singletons, right? And there were none of them, and so there were no types that were being used as singleton types. Okay. So what I think interesting is here is, particularly in Antler here, you see that there are, 63 types make up 606 components. So obviously each type is being used to sort of represent more than one concept from the application space. On the other hand, PMD here, we see 86 instantiated types, but only 146 components were identified. So in this case, we actually are using, more than one type to represent a single concept, right? And we similarly see some fairly wide variation. So FOP here has 53% of its types that get instantiated are singletons, right? And then you see Antler with none as well. Also, I thought it was interesting, the very high percentage of components that we identified that had immutable types only. So that really was like, hey, programmers really like immutable things. It's much easier to reason about than other stuff. And we're actually undercounting the immutable percentage because we don't actually look at user-defined types that are immutable. We only see system types that we know to be immutable. So this might be an undercount as well. So the next thing we sort of looked at was one of the more directed questions, which is, okay, how do programmers use a notion of building linked recursive data structures to sort of organize their program, or do they try and use aggregation? I have a set of objects, I have another set of objects that have pointers to this object, and I sort of aggregate and compose up. So in this example, we have one component that is marked as being recursive, this tree. We have 3 components that are marked as being sort of atomic or just simple aggregations. And then we have, since this component has 3 types, we have 3 types that are marked as being part of recursive data structures. And then since each of these has 1 type, we have 3 types that are marked as being aggregate types. So when we did these measurements over the programs, this is the ratios of the shapes per node or component. So we see that atomic is incredibly dominant. Like well over 90% of all the components end up being just simple aggregations. Now, this is a little biased because of the way we do indistinguishability. We say, oh, everything that's part of the same recursive backbone gets collapsed into one component, right? But still, this is saying that even in this case, you don't have the case where the programmer has lots of linked lists floating around the program, right? The programmer is building one recursive data structure or two recursive data structures. They might be getting collapsed down, but they're not using them all over in the code. They're using them in one or two places. So when we went and looked at types, this was kind of surprising, because now, especially like PMD here, right? If I flip back, you say, oh, okay, there is some cyclic structure component identified in PMD, but it's not heavily used. But here, over 50% of the types in PMD are involved in this recursive structure. And so we were a little confused, or I was confused by this. I was like, oh, great, I got a great bug. All right, let's go find out what my code's doing wrong. So we looked at PMD, and it turns out that, okay, so PMD actually is a Java source code analyzer, if I remember correctly. And so it builds a big recursive data structure for the entire Java source code parse tree. And so it has some class, I think it's like, Java, statement or something like that, Java node. And then it inherits from this in sort of a classic object-oriented style, one subclass for each type of node or statement that can occur in a Java program. So you'll see, Java while statement, Java if statement, Java expression statement, Java conditional statement, etc. And these are all linked into this one big data structure, which is the recursive structure that's being processed. And then each subtype will have some additional information that's specific to that particular type of abstract syntax tree node. And then these are built using sort of aggregation, and they'll hang off this tree in various ways. Right? So this is kind of interesting. And similar things in Antler and Xalan. We tended to see, there would be one very application-specific recursive data structure that the programmer had built because it was a very good representation of their problem domain. But in general, if there wasn't this strong need for building this structure, they much preferred just using aggregation and using built-in container libraries. So that was quite interesting to me, at least.
So do any of these applications have UI components, and are they frameworks that they interact with?
No, they've been pretty much stripped of their UI, so they're nice and easy to run from the command line. I can't really answer confidently about the framework stuff, although I didn't see a lot of framework code in there. I mean, stuff like Xalan is sort of framework code. It's a XML parser, right? And LU-index as well does text indexing. So they're sort of designed to be used, I think, by other applications. But they don't really depend on large amounts of sort of infrastructure or other framework themselves, from what I saw.
Didn't solve the problem of interactive input for testing, right?
Well, I think
so the
one
code,
thing is that
if there's code in there, it's not exercised, right?
One thing I think that you might conclude if you looked at that kind of code is that those kind of complex, deeply nested and sort of highly object-oriented frameworks would have a lot of types, basically, and they likely would be sort of in the same way that PMD has these abstract syntax trees that have all these different subtypes. You might see the same thing with the Windows with the UI code.
Yeah, I can see that. Okay, so the next thing we looked at were sort of these properties of the Indegree and local ownership. So in this case, obviously Indegree is pretty easy. This node has an Indegree of 3. This has an Indegree of 1. Not a problem. We discussed the local ownership a little bit. And so local ownership is defined as this edge or field, depending on how you're measuring, holds the pointer that is the unique pointer to the target object. Right? So in this case, none of these edges are going to be local owner edges because, one, there are multiple incoming edges to this. So that might mean they're sharing between pointers in different edges. And this edge is not a local owner edge because, well, it's non-injective. So that might mean there might be aliasing between two pointers that this edge represents. Whereas this edge is going to be a local owner edge because it's the unique incoming edge to this, and it's non-injective. So that means every pointer represented by this edge points to a unique object. Right? So if we go ahead and let's look at the Indegree distribution first. So this is the Indegree distribution per node or component. And as you expect, you sort of see, these are violin plots. So, and it's also logarithmically labeled. So basically you see that in this case, the Indegree of 1 or 2 is very, very prevalent, and it tails off rapidly as the Indegree gets higher. What's kind of funny is that over here, if you look at the Indegree, you see it isn't quite so clean. You see FOP has this funny little bulge here at about 3 or so, right? And this goes back, okay, and then, so this is the issue. I don't know if you remember from FOP, it had a huge number of singleton types, right? 57% or 55%. And so what it ended up doing is it declares all these singleton types, and then it places them all in a dictionary so that it can look them up quickly through other names. And so that means that each of these types basically has one incoming edge from the static reference and one incoming edge from the dictionary. So it gets this funny little bulge here. PMD has this goofy bulge here about 7 or 8. And this is from the fact that you have this large number of types building this abstract syntax tree, and then there are several references coming in to this abstract syntax tree, so they all get a slightly higher reference. But other than that, you see it mostly as you'd expect, tail off pretty quickly. You see a couple of types have just a sort of weird outlier number of references coming to them. These are usually singleton types. So this was nice. This sort of made sense and was consistent with what expectations would be. Then we have some other stuff. So here we look at the number of pointers, and this is measured in terms of the fields that have this property, that are internal. That is, they are building up one of these recursive data structures. And again, we see sort of even for PMD here, which had that large number of types, a relatively small number, about 10 or 15% of the fields, are actually used to build this very large recursive data structure. And if we look at the source code, we see that basically this recursive data structure is built mainly by the fields in the base class node, which has an array of sub-expressions, and then each sub-expression has a parent expression. So that the actual data structure and code that builds this very large recursive structure is fairly localized in this parent class, right? And then there's just a lot of code that does simple aggregation and manages these other auxiliary structures. Non-nullity, I mean, it's not too surprising. It sort of matches, I think, what people's expectations are. It's pretty prevalent that this field is never null in its invariant state. And then the local owner property, right? And so we see, okay, here, this is, I think, very interesting because it says ownership is something that we would expect programmers to strive for. Local ownership makes it easy to reason about things, makes writing programs safe, makes the reasoning local. And we see that, okay, yes, it is important, over 50%, a lot of benchmarks, but it's not universal. There are a lot of fields that are not always the local owners of their objects. The object they're pointing to is getting shared somehow, right? And so we need more than just this simple notion of ownership to really express what's going on in the heap. And keep in mind, this notion of local ownership is sort of implied by the classic notion of ownership types, right? So if this doesn't hold, then this is definitely not an owner field in the ownership type sense. So that means that ownership type ownership is even less than this, right? So the question is, where is all this sharing occurring? Yeah.
So when you say per field, you mean that you classify a particular source field as, say, non-null in every heap that you have in your snapshot?
Yes.
Okay.
Right.
So then I'm not sure about the internal measurement, because as you're building up a recursive structure, I think you will, once you find that if it only consists of 1 or 2 nodes yet, and maybe they're different type, that you will not yet classify, you will not collapse it yet and not classify one of these edges as internal. If it's a small, and only once you start seeing more nodes will you start classifying it as internal, which means you will reduce that number artificially very much, right?
Right. Actually, we do it the other way. So if we ever see it involved in a recursive data structure, we say it's involved in some internal. Yes, yeah. So the quantification goes both ways. It's a little weird, but we always try and pick the one that sort of biases the right way. So, yeah. Okay. So back to this ownership. So there are 2 ways that the local owner something could be shared or this local owner property could be violated. Again, because you could have non-injectivity, or because you could have multiple incoming edges. So the easy question to answer is, how frequent is this injectivity? Remember, I said this is a really strong property, right? So here's the rate of injectivity per edge that we see. So blue is the number of edges that are injective, right? It's over 85% in every benchmark, right? And in most cases where we see an edge is non-injective, it's because it points, the target objects are immutable, so like strings or something, in which case, If you're sharing strings, who really cares? Right? They're immutable. And if we include just this, then over 90% of the edges in every benchmark are injective. So that means despite being about the strongest aliasing property you could assert on these edges, it's almost universal, right? Which is fairly surprising to me. Now, the question is, does that hold for fields as well? And yes, it does. Again, we see that this sharing on immutable is a fairly common idiom, right? Here, like 30 or 40% of the fields in ANTLR are non-injective, but they're non-injective on immutable objects, mainly strings. But once you include that, still almost 90% of the fields end up being classified as injective or injective on immutable. So this is a really strong property in the type sense as well. So this means that the local ownership is almost never violated by non-injective edges. It has to be violated by this high in degree. So I really like this. I thought this was a great result. And I'm curious to see if anybody doesn't believe me. Okay.
Well, it seems clear that if you have aliasing to different parts of the list, that's confusing, I guess, a data structure. And that if you're going to use some list in multiple places, you would alias at the top, right? So is that the intuition here?
I'm not quite clear. So basically what this says is that you never see, you always end up sharing from, this list and that list both share the same objects. Very rarely do you have one list and you have a bunch of sharing from the pointers just in the same list.
So if you're going to share, for example, you're indexing some list two different ways to speed up search, right? But mostly you're not going to share?
Well, so what you're saying is if I'm going to index a list in two different ways to speed up search, I probably won't make two copies of the same elements. The first half I'll index one way and the second half I'll index the other way that share. I'll take two lists and make two copies in two distinct lists that have two different roles in the program and do the sharing that way. Yes, exactly. And so when we go and we actually do this edge categorization, so we're going to look at how many cross edges, right? We see that, okay, the tree edges, which are sort of a prerequisite for this local ownership, are high, but again, not universal. But the cross edges are pretty prevalent, right? And this says, yes, this sharing comes from, two different components that have objects playing two different roles that are sharing some common state that they need to either both reason about or reflect changes through. So we see that, okay, this cross-edge thing occurs fairly frequently, and this is where the non-ownership comes from. And so the question then is, is these cross edges, are they just created arbitrarily, or are there general sort of idioms that programmers use? Okay, and we see by field, about the same ratio. Or are there some idioms that programmers generally use to sort of do this sharing in a relatively controlled way or a standard way to make it easier to reason about? So here I show the number of cross edges we found in each benchmark with the sort of the min-max there for easy summarization. We looked at the number of cross edges that were cross edges on immutable objects. So we see that, again, programmers like immutable objects because it's safe to share them. They don't have to worry about how these, they can't change, so they don't have to worry about sudden, unexpected changes. We also see that, a fair number of programs end up doing a lot of sharing on singleton objects and also these objects in global intern tables, which is good because, that's sort of the point of a singleton object is everybody to share it. We also looked a little bit at this notion of local escape, right? And so we saw a lot of programs, which I think go back to sort of your question, where I have an object. It has, let's say, a list of things it stores. And then it also wants to be able to look them up quickly by key. So it also has a hash table of things it stores, right? And so really the sharing is all reasoned about locally in the parent object, which just has a vector and, say, a hash table, or an object that has a vector of possible pen colors and a pointer called current pen color, and they share, but it's very local. And so we saw this as a fairly common idiom, especially like an LU index, like 10% of the cross edges were on this. And so when we sort of looked at all the sharing that occurred in these categories, we ended up with a relatively low percentage of things that were sort of remained unclassified, or that the sharing was just sort of general or done in a way that was looked fairly specific to the particular application that the programmer was implementing. So this was pretty nice. That said, hey, look, a lot of the sharing is sort of idiomatic. It's well behaved. It's done in a standard way so that it's easier to reason about. If we looked at it, the number of fields, the cross edges per field, we saw a relatively sort of similar behavior, right? Leaving about 4 to 16% of fields having some sharing that couldn't be classified by one of these fairly basic idioms. So the question is, we made this hypothesis at the beginning about these roles and components, right? And the issue is, if this hypothesis was invalid, right, we could be grouping objects in just sort of arbitrary ways that mixed objects that had different behaviors together in the same equivalence class, and was going to cause us to lose fidelity in our measurements. But we see that in most cases we have a very high information classification, injective. That gives us an incredible amount of aliasing information, and non-injective, which basically gives us no aliasing information. We saw that in general we were very highly biased towards the high information content measurement fairly consistently, and this high information content bias was usually the sort of more natural one from a programmer perspective. So we feel fairly confident that our notion of roles and components is probably a good way to sort of map well to programmer intent, but fairly certain that it also is not destroying a lot of information and causing us to lose a lot of fidelity, right? So we're fairly confident that the results we have here are, representative, fairly precise, and meaningful, and this hypothesis is not throwing in a lot of spurious imprecision. So the conclusion, well, my conclusion at least. Oh, sorry, did you have a question?
So I guess one question about this injectivity property is, so obviously you want to take advantage of it, right? And
right.
You want to reason statically about that property.
Right.
So how would that work?
I don't know. That's the problem, right? I mean, that thing, it's very strong.
Yeah.
This notion of roles maps well to sort of programmer intent, but there's no nice token in the source code that says all these objects have the same role, so they should be in the same component, right? I mean, that's not clear. So the question is, how do you take this property, which is on sort of an aggregation of objects which play the same role, and map that into the declaration of each object so that you can say, this guy, when he's in with objects of the same role, is going to be very well behaved, but something. And I don't know what that is yet. I mean,
ownership types, you can declare it in the type system. And so ownership types give you that, but people don't have those in their languages right now.
Yeah, well, and I'm not clear.
Yeah, I don't think it's the same either, necessarily, right? I mean, because I think,
Why?
From what I see it, you're reasoning locally and say, look, I have a bunch of pointers here locally. There may be other pointers somewhere else that point this up, but locally, I know that my pointers will never alias, right? I mean, and that's a nice property. It's not the same as ownership, right?
And also, it seems to be sort of organic, right? I mean, I don't think the programmer has in mind this set of objects is, the same conceptual component. I think it happens organically through sort of the grouping of you get through containers. They say, I have a container. This container has pointers to blah, and they're sort of implicitly making this statement, but I don't think it's necessarily clear. So I think if you want to attack it from the source code perspective, adding annotations to containers is the way to do it, but I don't know the answer. So I'll mention that a little bit in my slide after this one. So my conclusion, I think there are lots of conclusions that people can draw, and I'd be interested to hear what conclusions other people draw. But I say, hey, look, this is really cool. I'm really excited about this. This means the heap is not this wild, woolly, horrible object, at least from a certain perspective. But recursive structures, not that common. I mean, a lot of reasoning is aggregate. So if you really have a decent way to reason about aggregate structures, you're in good shape. And the decomposition we do does a pretty good job of isolating these recursive structures so that they're in a small little chunk, and maybe you can bring some more powerful reasoning directed to them. That's great. Ownership is important, but it's not universal. So it's important to have some way to reason about this. But the nice thing about the non-universality is that common idioms cover a lot of the stuff that isn't there. So you don't need this rich description system to talk about all of this. With a few simple properties, you can say, oh, let's put these in, and we get pretty good coverage of the sharing that does occur. And especially for the static analysis perspective, this idea that the conceptual component abstraction plus injectivity is a really effective sort of way to capture a lot of this information, expresses a lot of stuff, isolates these more complex structures, and that's really, I thought was really great from a static analysis perspective. So what I think the implications of this study are, for various bits of research. Well, I think there are clear applications for static analysis, because I like that, that says you should favor set-based reasoning, and you only really need a simple set of properties. And I've already incorporated this into some recent research, and not to be too modest, but I think the results are amazing, and I'm just thrilled with them. So they're phenomenal. But I think there are also some solid implications for type and annotation systems, right? That you really you don't need to design, at least to get some good initial start over being able to specify these structures. You don't need a huge, rich, complex system. You can pick a small set of simple properties that are fairly natural to programmers and hopefully give them these tools in a way that they can easily use them and express things and not be overwhelmed by, I don't understand the semantics of what this is trying to express. I don't understand how this should work. Something should be a singleton. That's great, right? I'm sharing this thing, but it's only on immutable types. I understand that as a programmer. It's an easy thing for me to write and understand, and if the system spits that back out at me, I know what it means. Other areas, this is stuff I don't have so much experience with or I haven't thought about in such detail. Software quality metrics, right? This is a big question. We measured these structures over programs that are relatively bug-free, that are relatively mature, that are relatively well-tested. Do these metrics vary greatly if you have lower quality software, higher quality software? Does a high degree of sharing correspond to higher defect rates in something? I'm not clear on this. Memory management. There's some interesting structural information here that might be useful in coming up with some different memory management stuff. Program optimization, of course. If you know that a lot of these structures don't have aliasing, maybe you want to try and be a little more aggressive in doing some optimizations that would benefit from this. So let's see. Thanks, everybody, for coming. I think that's it, and I have a little time for questions. And we do have a tech report up. It's an MSR tech report. It's collecting a heap of shapes. So if people are interested, I can email it to you, or you should be able to find it pretty easily. Other than that, thanks a lot for your attention, and I'm happy to answer any questions or comments or whatever. Yeah.
So on the surface, it reminds me a lot of this kind of surprising result with the data structure analysis work, where they basically said they could build these separate heaps. They could put stuff in them. There wouldn't be pointers except from certain places into those heaps.
Yeah.
And that was all through static analysis, which is even like, wow, in C, right? So
yeah.
It's sort of like it just piles on the surprises. So. But I have to say, I never really trusted that work, and part of it is that it was only for a certain set of programs. It was I don't think they had a good result, say, for GCC, which is kind of like, I think it's kind of like that's a nitty-gritty program.
Yeah.
And I think the same thing. This is very interesting, and it's surprising to some extent. I think the big question I would have is does it if you look at bigger programs, if you go beyond. Those are interesting programs, but I don't necessarily think they're common .NET programs. A lot of the .NET programs use frameworks, they use UIs, they use, I would say like Eclipse a result for Eclipse would make my heart feel better, warm my heart.
Wouldn't the larger a program be require sort of more encapsulation?
Almost. You'd think.
More extreme, right?
Yeah.
So maybe it would be a great result.
Right.
But I'm just sort of like.
No, I think there's an issue.
You'd have, in order to get that information, you'd have to drive the benchmarks differently. You'd have to drive them by hand, because otherwise you're not using the user interface, right?
You're talking about Eclipse, right? You have to
For example, Eclipse, but anything that uses all these frameworks usually has a user interface with it that is making all those things happen. Right?
It's true.
How much slowdown did you see when you ran these?
A lot.
Infinity.
So when you get instrumented version that you can get.
No, okay, so the very fortunate thing was I was a little nervous when we started this, because basically we're doing DICON style invariance, right? We're computing likely class invariance for these objects. And, when I read the DICON work, or my takeaway from it was, yeah, it generates a lot of invariance, and a lot of them aren't that meaningful, right? It just generates a lot of stuff. And so I was concerned that we would really have to sample these with a really, really high rate to sort of get rid of all this, spurious invariant stuff. But what was really, kind of reassuring to me is that these structural invariants were pretty much universal. Like we would take 2 snapshots of a method call, And then every snapshot we would take after that would pretty much not be changing, right?
You could have low enough sampling rate to answer Catherine's point, which is you could produce instrumented forms of these programs and let people use them and rely on them.
It wouldn't be that fast. I mean, it still took me like, 6 hours to run some of the larger things, right? But, it wasn't as horrible as I was expecting to set it for a week and go home, take a vacation. Yeah.
I think that depends on the vocabulary that you use for positing liking invariants. I think in the original DICON work, they were using arithmetic. And
right.
It's very explosive, the number of terms you can construct.
Yeah.
Whereas here, I think you have deliberately
We've picked simple
restricted your
terms.
vocabulary.
Yeah, but I think also it's a reflection that programmers they want to have objects that are very invariant. They don't want to have a lot of exciting stuff going on in general. So, they say, this is the structure, and maybe we have 2 or 3 variations on it, this sort of type state thing, but really we try not to be too creative, because then the reasoning becomes all non-local for the developer, and that's just gets unpleasant quickly.
So you had a result where you had the number of types greater than the number of instances?
Yes.
But how can that happen if you're...
So that was for PMD, right? And this is where you have that huge tree that's made up of all the subtypes, right? And these all get compressed down into one component. So this component has something like 62 types associated with it, right? So
but they're all in the same data structure and they're
they're
just
all in the
like,
same data structure. Yeah.
It's a while or it's a for.
Yeah.
Okay, I get it. So is there some, okay, I now get that ownership is different from, what's the property you're saying if you're uniquely pointing out?
So the injectivity?
Injectivity?
Yeah.
So it's non-ejective?
So non-injective is this edge might have some sharing in it.
Okay.
Injective is it's basically like a function. We're saying that the function from one set to the other on this edge label is injective.
Okay, so injective is a property of the outgoing pointer, where ownership is a property of the incoming pointer.
No, so ownership would be the outgoing pointer as well, right? It would say this edge consists of pointers that always point to objects that they're the only pointer to.
But then you're saying
sure.
this
Okay,
object has no other pointers. So that's saying that coming in is one object, and so by
Right, so-
definition, only one person can point to you if you only have one incoming pointer, right?
So injectivity is basically a property of the pointer and the source object, whereas the ownership is, requires multiple objects in a little bit wider context. Yes, yes, yeah.
So can you make any measurements, observations about how well the heap is partitioned into things that have no pointers between them, only top level things? So whether you need like one heap or is there some notion of you can have multiple heaps?
Yes, now that you mention that, I think we were supposed to measure that and I didn't. Why didn't I do that, Chris?
I think that's called paper deadline.
Yes, okay. So I think initially we wanted to do this and basically look at sort of this notion of sort of clique size or graph span or whatever. But from my personal experience, what I can tell you is that you tend to see things chunk apart fairly well into modules. And then what you'll see is down at the bottom, there'll be these singleton types or strings that everybody ends up sharing. So you sort of see this tree-like structure where everybody continues to isolate out little boxes and then merges at the bottom. And what you'll also see sometimes is sort of some scary back references that create huge connections between large chunks of the structure, which sort of terrifies me. Like in Antler, I mean, I guess it's part of the way that the program has to work, but it certainly was scary to be like, in DGML you can say, show me the strongly connected components, and it highlights them in red. I don't know if anybody's played around with that. So I say, show me the strong, and it just highlights the whole graph, and I was like, oh God, this is not good looking.
But they still may be doing it in a systematic fashion. It's just not recognized by.
Yeah, it's just not captured. I mean, I think that's the other thing. We need to look at this back edge issue a little more, right?
So if things are so simple, why are we so stuck in the static analysis world?
I don't know. I mean, that's sort of what this was to ask about. And so I think one of the questions was, people come up with all these properties, right?
Dynamic analysis.
I mean, people come up with all these properties, right? And they're very, rich properties and very sophisticated things, right? But my feeling was, and this is what I did, I sat down and I read these papers, and then I looked at source examples, and I said, oh, what do I need to reason about these, right? And I feel like the things that I was coming up with these toy examples were more because they were such small examples, could be more complicated than what programmers did in practice, because they just wanted to write the simplest thing that was obvious and worked. Right.
So I have a deeper answer to that. Because in static analysis, you have to look inside the methods, and the intermediate state is very confusing.
Because of willy-nilly references from local variables to this or that.
That's right, because you like basically throw all the pointers up and then you put them back the way they're supposed to be put back together. And so it's that local internal state that screws up static analysis.
Right, and he was not measuring that.
Yeah,
That's right.
Only at the boundary,
So-
local variables excluded.
Okay, so I want to have one comment on that. So I definitely agree that the local state is more complicated, but one of the questions you have is in C++, you see the idiom, you have to know who the owner is, and someone has to dispose of the object. So there's a lot more. I'm going to take the object, I'm going to move it from this container to that container, and you now become the owner, right? In these object-oriented programs, there's been some interesting work saying the behavior of these is actually mostly functional, right? I don't transfer ownership so much as I create copies, and I create new objects, and I assign the fields once or twice, or I don't move this object from here to here. I just create a new object and overwrite it. So they're sort of mostly functional. And so this was the other thing that we used in the static analysis work. And we said, look, if we know these structural properties are well behaved, and if we assume that most of the updates are these sort of mostly functional type of updates, that means weak updates in general are fine, right? We don't need all this strong update machinery. We don't need case splitting. We don't need to do path sensitivity. We don't need to do all of this. And how much precision is this going to cost us in practice on these programs? And so we went and ran this, and basically we see very little information is lost by just using weak updates in these object-oriented programs, right? So we're almost as precise as we were when I had the case splitting and the strong updates and the path sensitivity, and it's much simpler and much faster. Or it's nice to analyze object-oriented languages with garbage collection rather than C++, which is painful, right?
You can take the local state and have an assertion or something. Like, so what we did in the collections work with Dimitris Pratos at Popple this year, we used 3-valued logic to try to capture properties of collections to get rid of synchronization, right? That was our optimization problem.
Okay.
And what the huge difficulty was always the internal state. And so in some cases, we just asserted after for some method that confused the internal state what was true at that point, and then the pointer analysis worked. Then the shape analysis worked.
And I think this is really important. I mean, in the static analysis work I was mentioning earlier, we basically took containers and we treated them as ideal algebraic data types. So we don't actually have the analysis explore the internals of the container representation, which, as you say, is very complicated. They do lots of pointer swapping and whatnot, and we just say an add takes a pointer and puts it in magically, right? And otherwise it's an opaque thing to the analysis, just like it is to the user. And that was really important as well, and it makes it much simpler.
So this is some other static analysis work that you have done?
Yes, yes.
That was his thesis work, was static analysis.
Yeah, and so this is a continuation of it. We just finished it up this summer, and so it's...
The big difference is in static analysis, you allow only evidence that you can prove. Like, you want to prove things about the programs, and that's the only evidence you allow in. Here, you sample the heap at runtime, you look at the actual thing. You can't prove anything about it, but apparently you don't need to. You can just...
but I think there's some... I mean, I think there's some interesting implications here from the annotation
garbage
perspective.
collector is looking at the heap all the time, right? So you have assertions on the heap because of that, right?
Yeah. And so,
but I really like your trick for doing it at method entry and then knowing what is, like that's a problem we never solved in Maria's work, is you ran out of memory because we took heap snapshots based at the garbage collector.
Right.
So we stopped at random points when the heap could be thrown up in the air, and we just statistically kind of ignored that, right?
yeah, Tom?
I think there is still some more to explore, though. I mean, there's a lot of good news, but your percentages for the cross edges that weren't classified were still pretty high when you compared them as a fraction of the min-max at the top, right? The cross.
Yes, yeah.
Right. So and I think that's the issue when you're like talking to people who are designing type systems. Well, you can say, oh, we can capture these patterns, but then the things that you don't capture, they can cause just untold pain if they don't. If your type system is too
so I think
restrictive.
this is the interesting thing between type systems, where I need to have a consistent type at every program point, versus this sort of, I think, which is interesting, is the annotation system, which is I can want to specify as precisely as possible, leaving this sort of unknown value permissible at invariant states, right? And I think this is really nice from the static analysis point, where you say, look, I can basically tell you that really at these, method entry and method exit, you're in a well-behaved.
Designed by contract and sort of the classic, what we've been doing.
Right, and I think basically this informs, like, if you have design by contract, what things should be really easy to express in the contract language. And if you can express these simply, then it becomes much easier to use this contract language for a programmer, because they have simple things they can write down that are very important to them, right? You still have this, this is if you want a complete system, this is a non-trivial percentage that you still need to fight. But that means that, in a much smaller percentage of the time does the architect or the person who really thinks about the way the program is designed have to sit down and write some non-trivial specification of what's happening. Usually it's one line, boom, it's shares unimmutable, easy.
Clearly they don't want to do it that way, too. In some sense, that's a good place to look to fix the program, because ultimately, it's just hard to reason about.
Right. So if you add pain where you don't want them to do that, then that's good, right? Then they don't do that.
So is there a related work on finding annotations, that go along the lines that you have, where you say you have this component, which contains this type of object?
In my static analysis, I've mined these specifications. I'm still not happy with the way to output these. I think this is the next thing I really want to work on, is what's a good way to express these usefully, right? That I can extract lots of information, but what's actually useful to give the programmer, what's useful to specify, provide to other tools. And so, that's the other thing I was interested in talking with some people here, is I say, look, here's a good way to categorize these things. In my static analysis, I can actually quickly, in real programs, identify these things. And is this information sufficient to give you the ability to do modular reasoning in given methods for the kind of things you want to reason about? Or is there stuff that's missing? Or what else do you need? This kind of, I think this is a really interesting thing. You have this analysis which makes gross simplifications for, in a sense, right? Weak updates everywhere, right? So obviously I'm going to lose information in certain places. There's code that does strong updates that I'm going to lose information on. But I can propagate pretty quickly throughout things. I can do a pretty good job. So I can get you these sort of global invariants, so you can then do local reasoning about sophisticated heap manipulation, right? And what's a good way to sort of coordinate on that, and what's useful here? I don't know the answers to that, so I'd really like to talk with people about it. Okay, anything else? All right, great. Thanks, everybody. Appreciate it.